and welcome back. In this video, we're going to look at correlation. So consider the two scatter plots which show the relationship between the lengths and the rides durations for 40 roller coasters from around the world. When you look at the two scatter plots, you can see that the length on this scatter plot is in feet and the length is measured in meters on the right. And then the duration on the left is in seconds and the duration on the right is in minutes. Notice that when I change the axes, scales, that the scatter plot, the form, and the direction did not change, okay? So we can clearly see the direction, which is positive, and the form, which is fairly linear, of both scatter plots. But what about the strength? Like, how strong is their relationship? We're gonna look at something called correlation, and correlation measures the strength and direction of a linear association between two quantitative variables. And that's really important. So if your relationship is not linear, correlation's kind of meaningless. Here's a famous correlation coefficient. Okay, so the symbol we use for correlation is the letter R. And the way we find it is, this looks familiar, I'm sure. It's the sum of the standardized X values times the standardized Y values. And then we divide that by the sample size minus 1. So it's a very tedious calculation. Your calculator, luckily, will give you a correlation coefficient value, which is the letter R. Before you use correlation, though, you want to check the following. You want to check the quantitative variables condition because it measures the strength and direction of a linear association between two quantitative variables. Make sure it's straight enough, so that takes care of the linear component of that definition. Also, you don't want any outliers, okay, that are extreme. Correlation has some properties. So the sign tells us what direction the association is, if it's positive or negative. And remember, positive just means, for the most part, it's increasing, and then negative means it's going down towards the right. Correlation is a value that's always between -1 and 1, inclusive. So you can never have a correlation of, 1.5. A correlation of -1 and 1 are the same strength. It's just the negative tells us the direction is going negatively, so it's decreasing, and +1 tells us that it's increasing in the positive direction. But both are equal strengths. They would mean perfect linear relationship or association. Correlation treats X and Y symmetrically. So the correlation of Y with X is the same as X with Y. Correlation has no units. And it's not affected by changes in the center or the scale. And as you could see in our scatter plots above, right, the scale changed and it did not affect the scatter plot form, and the correlation would have stayed the same. And again, just remember, correlation measures the what? The strength of what kind of association? Linear, between, and measures the strength and direction of a linear association between two quantitative variables. Correlation is sensitive to outliers, just like the mean. Okay, please pause the video and recall the scatter plots that we looked at in the previous video, A through D. The correlation for these plots, respectively, are 0.614, -0.791, -0.388, and -0.040. You want to check your conditions for using correlation, and if you feel they're satisfied, interpret the correlation. And then when you're ready to go over this, you can unpause the video. So here we know that the correlation is 0.614, okay, for this first one. So if I go through my conditions, here's my 3 conditions I want to go over. is this quantitative data? Well, cost is quantitative and food costs is quantitative. So that's important. It is fairly linear. And there's maybe one or two outliers, but not bad. They will affect the correlation. So correlation is appropriate. And here I would say it's moderately strong. Now, there is really no set rule for weak, moderate, and strong because depending on, what field you're in statistics, we could have a correlation of point two, and that's very weak. But if you're dealing with like social sciences or you're in some other field, point two could be considered a great correlation. It could be moderately strong. So it just really depends. If I look at letter B, the correlation is negative 0.791. However, when you check your conditions, even though you have two quantitative variables, wage and hours to earn an iPhone, you can see that it's not linear. So for this one, I'm going to make a little note that correlation is not appropriate because the form is not straight. Okay, it's not linear. You can see it bends, and we kind of discussed that in the last video. And then here we have the checking the three conditions again. It is quantitative, two quantitative variables. It is linear, okay, although a very weak correlation, as you can see, and it's in the negative direction, which is why the correlation is negative. So again, that negative just means that it's, as x is increasing, y is decreasing. So it's going in a negative direction. And it would be appropriate to discuss correlation. And in letter D, the correlation is negative 0.040. So as you can barely tell that this has a negative correlation. More importantly, the correlation is really close to zero. So the closer correlation is to zero, the less related the two variables are. The closer the correlation is to 1 or negative 1 means that there's a strong linear association, right? So a correlation of 0 means no association, but a correlation of either negative 1 or 1 means it has a perfect linear association, which in real life, it's very difficult. I would be very suspicious if I had two variables that I was analyzing and their correlation came out to a negative 1 or a positive 1, especially for a large data set. Okay. The table displays the average unit value dollars per pound of almonds and pistachios that were exported from the United States from 2010 to 2021. The table also shows the years because that's part of the data set and can be interesting, but we're going to use only the two other variables. So we're just going to look at almonds and pistachios. Use technology to find the correlation. Okay, so what I need to do is I need to go into my calculator, and again, we're entering data. So go to stat and then edit. And then the part in this ad, it will close here shortly. There we go. Okay, I want to clear out what's in here. So I'm going to hit clear and then clear. And I'm going to come down in L1 and I'm going to enter in the almonds. So let's do 1.77. And since I'm finding correlation, it doesn't matter whether I have almonds for my explanatory or my response variable, because remember, one of the properties of correlations is it's symmetric. So that's why we don't really care in this case. So in case you're wondering, why am I plugging in almonds into the table? It's not because it's first in the table, because you do want to be careful with that. Sometimes, just because it's the first row on the table doesn't mean it's automatically X. It could be Y. You want to ask yourself which one is the response, that's your Y, which one's the predictor X. But here it doesn't matter because we're just looking at correlation. So okay, so I must have missed a number because I have a missing, like an extra line. So let's see here. This should be, I'm going to work backwards. This should be 1.94. Okay, and then it was 2.64. And then it was 2.67. Okay, so now everything seems like it's okay. All right, so in order to find the correlation, this is what you need to do. I need to turn on what's called the diagnostic. So to do that, I need to go into the catalog. You're gonna hit the blue button and then hit 0 for catalog. And the best way to go to catalog is to do alpha C. So hit the alpha button and then the letter C. It's right where the magnifying glass is. And it's going to take you down. Or you can just scroll all the way down, which sometimes, alpha D for diagnostic. Okay, so there's my catalog, and maybe this calculator doesn't have diagnostic on. For some reason, I don't see it in here. Okay, so what I will do, I'll get my handheld calculator, so bear with me. And I'm going to have to type in the values here. So I'll show the screen here in a second once I type in my values. So give me a second to do this. And again, I apologize. I don't know why diagnostic wouldn't be in there. So you're gonna hear some silence for a little bit. It's a good time for a stretch or go run to the refrigerator and get a soda or a snack or something healthy while I type these in. Okay, so I'm going to attempt to put on my camera so that you all can see what I'm doing here. Okay, so I entered in my data. I want to turn the diagnostic on. So to do that, I'm going to go to second and then catalog. It's where the 0 is. Okay, and the catalog comes up, and you can either scroll down to diagnostic on, or you can hit the alpha button, which is the green button, and then the D. Okay, and sometimes you have to hit it twice, so alpha D. And see, it scrolls all the way to the Ds, and you just have to go to diagnostic on. So you're gonna click enter, and then click enter again, and make sure it says done. Now when you get the correlation, it'll pop up for you. So what I want to do now is, in order to find correlation, remember I need to check my 3 things. I need to make sure it's quantitative data, which it is. It's almonds and pistachios in dollars per pound. So that's numbers with units. I need to check to make sure it's linear and make sure there's no extreme outliers. So I have to check my scatter plot. Remember how to do that? If not, it's discussed in the last video. You're going to go to second, y equals, turn the plot on. And right now mine is box plot, so I want to change the type to Scatterplot, which is the first. And then you just go to zoom 9. And it's going to graph that. Okay, I have a box plot there, so that means one of my plots is turned on. So you can turn it off. You can see my plot 2 is turned on. So just hit enter and turn it off if that happens. Okay, now go to zoom 9 and you'll see just the scatter plot. So it looks fairly linear to me. I don't see any extreme outliers, like maybe that could be an outlier right there, but it's fairly linear. So it's good to try to find the correlation. So how do I find the correlation? And I will write this down for you. You're going to go to stat, and then you're going to go to calc, and you're going to pick number 4. You're doing a linear regression, ax plus b, okay? So, or you can choose number 8, which is what I'm going to choose, linear regression a plus bx. Okay, that's the one we're going to use. And then just make sure your x list is in L1, your y list is in L2, and then you can just go to calculate. And then there are some values which we're going to discuss in the next chapter, so a and b. And that's if we want to write our regression line, okay, but we're not there yet. There's another value r squared, which we're going to look at in the next chapter, but there's what we need is r, which is your correlation coefficient. And the correlation coefficient's 0.86, so that's pretty strong. That means there's a strong linear relationship between the dollars per pound of almonds and the dollars per pound in pistachios. Okay, so there's some relationship there between those two things. Okay, so 0.86 is your correlation. So let me write out for you here what we did. So we went to second, catalog, and then we turned on the diagnostic. So turn diagnostic on, make sure you hit enter and enter so that it says done. And then of course you're going to enter the data into L1 and L2. I'm just going to put here, check your conditions. And then to find the correlation, you're going to go to stat and then go to calc and then choose number 8. We're going to do linear regression, a plus bx, and then enter, and you'll see the correlation is 0.86, which is strong. So there's a strong linear relationship between almonds and pistachios and their cost. Okay, please pause the video and take a look at the next problem and then unpause when you're ready. Several measures of prices and wages in cities around the world show a variety of relationships, some of which we can summarize with correlations. Suppose that instead of measuring prices in the US dollars and recording work time in hours, we had euros and minutes. How would those changes affect the conditions, the values of correlation, or our interpretation of the relationships between those variables? So it wouldn't. Remember, correlation is based on standardized values, right? Z-scores. And the conditions, the value of the correlation, and the interpretation are all unaffected by changes in units. Something I want to caution everybody on is, warning, correlation does not equal causation. So just because there's a strong correlation between two quantitative variables does not mean the predictor caused the response to change. Okay, that's very important to remember. A hidden variable that stands behind a relationship and determines it by simultaneously affecting the other two variables is called a lurking variable. Scatter plots and correlation coefficients never prove causation. Here's an example. When ice cream sales increase, drownings increase. Okay, does this mean ice cream causes drownings? Take a minute and pause the video and think about that question and answer, and then unpause when you're ready. Okay, so hopefully you said no, that ice cream does not cause drownings, right? What actually could cause drownings? Well, there's a lurking variable there, right? It's a variable that's kind of hidden, that's influencing the relationship in some way. And the lurking variable there could be either temperature or time of year, right? So when more people, when the weather's warmer, more people are probably swimming, right? And when the weather's warmer, more people are eating ice cream. So if you graphed ice cream sales and drownings, you would see that there would be some type of relationship, but it doesn't mean that ice cream causes drownings. It's more so because of the time of year, that we see that relationship between the two. So again, correlation never means causation. And that's the end of the video. Please stay tuned for the next chapter, chapter 7, where we take the information we learned and we actually create models to represent these relationships, and we use the models to predict. So have a great day, everyone. If you have any questions, please let me know.